Yeah, good morning everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of EC at IARE, Hyderabad. Today we will be discussing about time domain analysis of discrete time systems. Here, these are the contents. Discrete time system equations, E operator, response of linear discrete time systems, useful signal operations, response of linear discrete time systems, zero input and zero output response. After that, convolution sum. We will verify that procedures or in terms of the graphical and other result related, like graphical procedure for the convolution sum. After that, finally, we will analyze that classical solution of the linear difference equations. So here, the time domain analysis of the discrete time systems, DTS, we know that all background of the CTS, continuous time signal and discrete time signal with reference to that system also, right, to verify that time domain analysis of discrete time systems. Okay. So here discrete time systems equations, there is a mathematical model, mathematical background for this. We have to follow that advanced operator form. The operator form is mathematically it is available y of k plus 1 plus an minus y a1 an minus 1 and y of k plus what do you call k plus 1 minus 1 and so on. Okay, it is represented what do you call a1 y of k plus 1 y of plus a naught y of k is equal to bm f of k plus m plus bm minus 1 f of k plus m minus 1 and so on. b1 f k plus 1 plus b naught f of k. So the left hand side of this form, as per this discrete time system equation, we are considering that advanced operator form. It consists of the output at instant. Here it is k, what do you call k plus 1, k plus n minus 1, and what do you call okay k plus 1, k plus 1 minus 2, and so on. Okay, so the right hand side of the equation, here it is right hand side of this equation from here to here, okay, consists of the input at the instants. So k plus 1, k plus m minus 1, okay, k plus m minus 2, and so on. Okay, k plus m minus 3, k plus k, what do you call, k plus m minus 4, and so on. Okay, so the condition that the above system is causal or casual is what do you call, we have seen this all are m less than or equal to n. Okay, with this, so for a general casual case or causal cases, okay, easily can verify that what do you call, m is equal to n. After that, the above system can be expressed as y of k plus 1 plus an minus 1 into what do you call y of k plus n minus 1, and so on. a1 y of k plus 1 plus a naught y of k. It is also equal to that bnf. Here it is. You can use that. I'll write the suffix bn f of k plus n and plus bn minus 1 f of k plus n minus 1. Okay, plus and so on. Okay, then. So if it is delay operator form in case of n, m is equal to, previously we have seen that m is equal to m less than or equal to n. After that we will consider that m is equal to n. We can replace by k minus 1 throughout the equation. Such a replacement is the delay operator form. But consider this mathematical notation. So like this is also equal to this one. It can be expressed as y of k, where it is y of k is equal to an minus 1. Okay, an minus 1, y of k minus 1 minus an minus 2 y k minus 2 minus and so on minus a naught y of k minus n plus bn f of k plus bn bn minus 1 f of k minus 1 plus and so on. It can be expressed as, so y of k is equal to minus an minus 1 y of k minus 1 minus an minus 2 y of k minus 2 minus and so on. Like this minus a naught y of k minus n plus bn f of k plus bn minus 1 f of k minus 1 and so on. Okay, there are the past n values of the output. Okay, you can consider y of k minus 1, y of k minus 2, y of k minus 3, y of k minus 4 and so on, y of k minus n. The past n values of the input f of k minus 1, f of k minus 2, f of k minus 3 and so on, f of k minus n, and the present value of the input f of k. Okay, this is you have considered that based on that advanced operator form under DTS, discrete time system mathematical model. Okay, so like this discrete time system equations, yeah, initially conditions are iterative solution of the difference equations. If the input is causal, the f of minus 1 is equal to f of minus 2 is equal to f of minus n is equal to 0, and we need only n initial condition, y of minus 1, y of minus 2 and so on, y of minus n. Yeah, this results allows us to compute iteratively or recursively the output y of 0, y of 1, y of 2, y of 3 and so on. For instant, to find that y of 0, we said k should be a 0 or k is 0. So the left hand side is y of 0 and the right hand side contains terms y of minus 1, y of minus 2, y of minus 3, y of minus 4 and so on, y of minus n. And the input f of 0, f of minus 1, f of minus 2, f of minus 3, f of minus 4 and so on, f of minus n. Okay, therefore, so we must know the n initial conditions. So based on that initial condition, y of minus 1, y of minus 2 and so on, y of minus n, to find y of 0, y of 1, y of 2, y of 3 and so on. Okay, so under this, the discrete DTS equation, initial condition, iterative solution of the difference equations. So we easily can analyze by using the simple example. Here it is, solve the iterative y of k equal to minus 0.5 y of k, y of k minus 1 is equal to f of k with initial condition is y of minus 1 is equal to 16, causal input f of k equal to k2. So with this, consider this is a simple example, easily analyze. You can solve this, rewrite the equation in the delay operator form and move all the past outputs to the left. Okay, that is y of k. Y of k is equal to j minus 0.5 y of k minus 1 is plus f of k. So here we obtain, but using this delay operator form and move all past outputs to the left, it is followed by where y of k, where y of k is equal to 0.5 y of k minus 1 plus f of k. So we obtain y of 0 is equal to 0.5 y of minus 1 plus f of 0 is equal to 0.5 16 plus 0 8. So if you are substituting in the 1, 0 is 8 and 1 0.5, here it is 0, here it is 1 and 8, here it is 2, so finally that 5. So like this, y of 2, y of 2 0.5, y of 1, y of 2, y of 5 and so on 6.5 here. So after that, y of 3 12.25. Okay, like this, where y of 4 22.125. So rewrite this equation delay operator form and move all the fast outputs to the left. So you can observe that y of 0, y of 1, y of 2, y of 3 and y of 4 and so on. Okay. So therefore y of 0 equal to 0.5 minus 1 plus f of 0 here and 5 and 6.5, 12.25 and 22.125. So like this graphically, that iterative solution of the difference, so k versus y of k, is you can analyze that from x-axis the k, y-axis the y of k, and 0 here it is, here we are applying that 0, that y of 0, that y of, here it is y of 0 like this, y of 0 and 8. Okay, next y of 1, the y of n, here it is a y of 1 here and 5 is like this, and y of 3, y of 2, where y of 2 here it is substituted, here it is based on this typical value, right, to verify that graphically, and y of 3 here and response is 12.25 and y of 4 and so on. Okay, like this, right, to analyze that time domain analysis of discrete time system. Okay, here to consider the next problem. Yeah, solve the iterative y of k plus 2 minus y of k plus 1 plus 0.24 y of k is equal to f of k plus 2 minus 2 f of k plus 1 with the simple condition y of minus 1 is equal to 2, y of minus 2 is equal to 1 and causal input f of k equal to k. So how we are verifying this one? We rewrite this equation in the delay operator form and move all past outputs to the left. Similar case here, where y of k is equal to, where y of k is equal to y of, so y of k y of k minus 1 minus plus minus 0.25 y of k minus 2 and y of k, okay, minus 2 f of k minus 1. We obtain y of 0. Okay, here it is like a similar case where it is substitute 1.76 y of 1. Y of 1 is equal to y of 0 minus 2.24 y of minus 1 plus y of f of 1 minus 2 f of 0 is equal to 1.76 minus 0.24 and 2 plus 1 minus 0, it is around 2.28. Typically write out to the y of 0. Y of 1. So y of 2, similar procedures, right, where for the 1.8576. Okay, so with this, yeah, the condition, the continuous time system, we obtain the operator, what do you call, the operator D to denote the operation of the differentiation. For discrete time system, we use the operator E to denote the operation for the advancing the sequence by what you call time unit. So thus it is mathematically it is available E of f of k is equal to f of k plus 1. E square and f of k is equal to f of k plus 2 and so on. the e power n f of k is equal to f of k plus n. Okay, for example, y of k plus 1 minus ay of k is equal to f of k plus 1, y of k minus ay of k is equal to e f of k, and e of a, y of k is equal to e of f of k. Okay, so this is related to what we call discrete DTS, response of the linear discrete time system. Okay, system response to internal condition where E operator. Okay, next under DTS, we would consider the same system, discrete time system, that equation E operator. In continuous time system, we used the operator D to denote the operation of the differentiation. This, for discrete time system, we use the operator E to denote the operation for advancing the sequence by one time unit. Thus, E of E into f of k is equal to f of k plus 1. Okay, E to f of k is equal to f of k plus 2. Okay, and so on. E3 f of k is equal to f of k plus 3, and so on. En f of k is equal to f of k plus n. Say for example, y of k plus 1 minus ay of k is equal to f of k plus 1. With this, e into y of k minus a into y of k is equal to e into f of k. Okay, so e minus a into y of k is equal to e f of k. So like this, for the second order difference equation, you have to consider this one. Okay, so where y of k plus 2 plus 1 by 4 y of k plus 1 plus 1 by 16 y of k is equal to f of k plus 2. So using this all, e square plus 1 by 4 e plus 1 by 16 into y of k is equal to e square f of k. Okay, so a general nth order difference equation where if a small n is equal to m can be expressed. So e power n plus a n minus 1 into e power n minus 1 plus and so on plus a1 e plus a naught into y of k is also equal to what you call this bn e power n plus bn minus 1 e power n minus 1 plus and so on plus b1 e plus b naught f of k. So your q of e of q of e into y of k is equal to p of e into f of k. So where e of e is equal to q of e is equal to e power n plus a n minus 1 into e power n minus 1 plus and so on plus a1 into e plus a naught. Similarly, the p of e is equal to bn into e power n plus bn minus 1 e power n minus 1 plus and so on plus b1 into e plus b naught. Okay, so like this, the DTS response of the linear discrete time system response to a internal condition is the operator is affected. With this, for the second order differential equation analysis based on general nth order difference equation where small n is equal to m can be expressed in a mathematical model. Okay, so for the second order difference equation, y of k plus 2 plus 14 into y of k plus 1 plus 1 by 16 y of k is equal to f of k plus 2. That means, so e2 plus 14e plus 1 by 16 into y of k is also equal to e into e2 into f of k. The general nth order difference equation n is equal to m can be expressed as what you call this value, and y of k is like this. If f of k qe, y of k is equal to pe into f of k, where we know that q of e and p of e. Okay, like this, the d operator will be okay. Analyze Yeah, like in similar to the continuous time cases, total response we know zero input response plus zero state response. From this condition, similar to the CTS continuous time case, here the zero input response y of k is the solution of the system with the condition what you call f of k equal to 0. Okay, that is E of q of e into y naught of k is equal to 0, or you can consider where e of n plus a n minus 1 into e power n minus 1 plus and so on plus a1 e plus a naught, it is product of this y of k is equal to 0. So y of y naught of k plus n plus a n minus 1 y naught of k plus n and minus 1 and so on. So a1 y of k plus 1 plus a naught y of k is equal to 0. Okay, like this the E operator similar to the continuous time case, total response is equal to 0 input response for 0 state response. Okay, from this the 0 input response y naught of k is the solution of the system with f of k is equal to 0. So that is q e of q into e of q of e into y naught of k is equal to 0, or you can consider what you call en plus what you call en minus 1 en to n minus 1 plus so on plus a1 e plus a naught into y of k naught equal to 0, or y of 0 k plus 1 plus an minus 1 y of 0 k plus n minus 1 and so on a1 a naught of k plus 1 plus a naught y of k is equal to 0. So the equation states that under this DTS discrete time system equations, it will be response of linear discrete time system response to internal condition. The internal condition is followed by the zero input response. The equation states that the linear condition of the y naught of 0 and advanced y naught of k is 0, not for some values of the k but for all k. Such situation is possible if and only if y naught of k and advanced y naught of k have the same form. Okay, this is true only for an exponential function gamma k into sense where gamma k plus m is equal to this value. Of that is you can assign this y naught of k and e square y naught of k and so on e power n y naught of k so on is you can analyze this one have the same form. This is true only for the exponential function. It's like this. After that we will expect that a response of linear discrete time system, the system responds to internal conditions, that is based on this the zero input response. Okay, so yeah, the zero input response, the equation states that linear combination of y naught of k and advanced y naught of k is 0, not for some values of k but for all k. Okay, such situation is possible if and only if y naught of k and advanced y naught of k have the same form. Okay, so this is the true only for exponential function yk, since y of k plus m is equal to y into my of into k. Therefore if y naught of k here y naught of k is equal to cy into k, so we have ey of naught of k is equal to y of y naught 0 k plus 1, cy k plus 1, and so on. So, and similarly that E2 and so on, En, that En, here it is, that En y naught of k is equal to y naught of k plus n is equal to what you call cy k plus n is equal to that cy n yk. Okay, like this we will analyze that the response of the linear discrete time system responds to internal conditions based on this the zero input responses. Okay, so using this the zero input response is followed by this particular equation where all are the roots of the polynomial, and where it is the characteristics polynomial of the system. So where it's the characteristics equation of the system are called characteristic roots or characteristics of characteristics value, or we can consider that also eigenvalues of the system. The exponential gamma ik, where I is equal to 1, 2, 3 and so on, n are characteristics. Characteristics modes are maybe natural mode of the particular system. Okay, so with this zero input response, substitution of this results to the system equation is C of yn, where that C of yn plus what you call an minus 1, yn minus 1 and so on. You can consider that a1 y plus a naught, okay, if the product is c y k is equal to 0. So for trivial solution of this equation, y of n and a minus 1 y n minus 1, like this, that is q y of 0 equal to q of y is an nth order. This is nothing but nth order polynomial, can be expressed in the factorized form assuming all distinct roots. You can consider that y of y minus y1, y minus y2, or maybe what you call y minus y1, okay, y minus y2, okay, and so on, y minus yn is equal to 0. Like this, where y has n solution y1 and y2 and so on yn, and the system has solution c1 yk1 and c2 yk2 and so on. So like this, with reference to the zero input response, substitution of this results to the system equation yields where c of is equal to 0, and the characteristics polynomial, characteristic equation of the system, characteristic roots are characteristic values, or we can consider the eigenvalues of the system. Easily can analyze that based on that zero input response will be appeared. The exponential or characteristics modes are natural mode of the particular system. Okay, it is based on the zero input response. Okay, based on this zero input response, repeated roots. If you are considering the repeated roots, if two or more roots are repeated, the form of the characteristics modes is modified, similar to the CTS or continuous time case. If a root repeats or times, the characteristics modes corresponding to these roots are gamma power k, gamma for k. If the characteristics equation of the system is like this, the zero input response of the system is where y naught of k equal to this one. Okay, so we have to consider one more, the complex roots. The zero input response based on the complex roots, as in the case of CTS, continuous time system, the complex roots of a discrete time system. Okay, yeah, the discrete time system must occur in the pair of the conjugate so that uh, the real form of the solution. First expression, the complex conjugative roots command star in the polar form. Based on this, the zero input response is ready to observe. Okay, for a real time system, C1 and C2 must be conjugate so that y naught of k is a real function of k. Okay, let us C1 is equal to C by 2 where C1 is equals to C by 2 e power j theta, and where C2 is equal to C by 2 into e power minus j theta. So by using this, you can calculate the y naught of k. Okay, so where c and theta are the arbitrary constants determined from the auxiliary conditions. It is all are based on a discrete time system equation based on the particular response of the linear discrete time system. The system responds to internal conditions with help of the zero input response. How it is affected with for a real system based on C1 and C2 must be conjugate so that y naught of k is real function of the k. So easily can analyze this real function of the k where c and theta are arbitrary constants determined from the auxiliary conditions. Okay, similarly for an LT linear time what you call system, discrete system described with a difference equation y of k plus 2 minus 0.6 y of k plus 1 minus 0.16 y of k is equal to 5 into f of k plus 2. Okay, find that the zero input response y naught of k of this system. The initial conditions are y of minus 1 is equal to 0, and what do you call that y of minus 2 is equal to approximately what you call 25 by 4. If it is the system equation in E operator form is, we know that E operator form is nothing but what you call E square minus 0.6 E minus 0.16 y of k is equal to 5 into E square into f of k. The characteristics equation, based on the characteristics equation, directly we have to substitute. The zero input response is y naught of k, okay, is equal to C1 into 0 minus 0.2 power k plus C2 of 0.8 per k power k. Okay, so like this, substitute that y naught of minus 1 is equal to 0, y naught of minus 2 is equal to 25 by 4. We obtain minus 5 C1 plus 5 by 4 into C2 is equal to 0. So 25 C1 plus 25 by 16 C2 is equal to 25 by 4. So C1 ready to substitute where C1 is equal to 1 by 5 and C2 is equal to 4 by 5. Therefore, so ready to calculate that y naught of k is equal to this particular 1 by 5. What you call minus 0.2 power k plus 4 by 5, 0.8 power k with k greater than or equal to 0. Okay, like this, the system specified by the equation. Okay, by using this equation, determine y naught of k. The zero input response is like this. After that, find this LTI-TD system described by the equation with the help of where the initial condition or y naught of minus 1 is equal to 2. We have to consider first. After that, y naught of y naught of minus 2 is equal to 1. That is based on these two conditions. Condition 1, the initial condition is y naught of minus 1. So how it is varies, how it is characteristics roots are changed or not. The input, the zero input response is ready to vary and not. After that, you can consider that y naught of minus 2 is equal to 1. Okay, here this where y naught of minus 1, okay, is equal to 2. We have to verify. After that, y naught of minus 2 is equal to 1. Okay, so like this, try to verify where this the characteristics roots are 0.78 plus or minus j 0.45, that is 0.9 into e power plus or minus j pi by 6, thus is 0.9, and where beta equal to pi by 6, and the zero input response is given by what you call y naught of k is equal to c into 0.9 or k into cos pi by 4 into k plus theta. Yes, substituting this initial condition y naught of k, okay, that condition, we know that condition. The condition is based on where y naught of k, y naught of minus 1, where y naught of minus 1 is equal to 2, and y2, y naught of minus 2, where y naught to minus 2. So here it is 1 we obtained, where c by 0.9 into cos of minus pi by 4, pi by 6 into cos minus sine of minus pi by 6 into sine theta. It's also equal to c by 0.9 square root of 3 by 2 cos theta plus 1 by 2 sine theta is equal to 2. Okay, this is under the zero input response under time domain analysis of discrete time system. Okay, and so go on verifying this. What do you call the characteristics roots of 0.78 plus or minus j 0.45, that what is the beta value, how it is varies, where y naught of k is ready to calculate with reference to these two conditions, where y naught of k equal to c into 0.9 power k cos into pi by 6 into k plus theta. If it is using this substituting the initial condition y naught of minus 1 and y naught of minus 2 is 2 and 1. Like this, gone what you can finalize this substitution, c by 0.9 square and minus pi by 3 plus theta, and is equal to c by 0.81 cos of minus pi by 3, okay, cos theta minus sine of pi by minus pi by 3, and so on. It is also equal to 1. Okay, with this, or we can consider the square root of 3 1 by 1.8 c cos theta plus 1 by 1.8 c into sine theta equal to 2. Similarly, 1 by 1 minus 1.62 into c cos theta plus square root of 3 by 1.62 into c sin theta is equal to 1. Like this, we have c into cos theta is equal to 2.308, and c sin theta is equal to minus 0.397. Then the theta ready to calculate. The theta is equal to tan inverse minus 0.39 by 397 by 2.308. So here it is finally minus 0.17 radians. Substitute that theta is equal to minus 0.17 radians in the c sin theta. The c sin theta is equal to 2.3088, c equal to 2.34. Okay, so of that y naught of k is equal to 2.34 of 0.9 power k into cos of 5 by 6 into k minus 0.17, where k greater than or equal to 0. This is under what you call the zero input response of DTS equations. Okay, like this, we have to verify that time domain analysis of discrete time. Okay, discrete time systems with the mathematical analysis. Based on this all analysis, we have to verify that what you call the discrete time systems with the DTS based on this response of a linear discrete time system based on the system response to internal conditions, zero input response. Okay, based on this zero input response, these can evaluate these all values maybe in terms of this. One is what you call the LTA LTD system with based on this. After that, zero input response is ready to measure. Okay, and so on. Finally, the time domain analysis of discrete time system (DTS) method analysis is finalized. Okay, so like this, we have to consider the time domain analysis of discrete time system is what you can analyze. It is proved by using a mathematical model. The zero input response is varied. Initial conditions are verified. Already we have done in mathematical modeling based on this time domain analysis of discrete time system. Okay.
Like, share and subscribe. Hit the bell icon for more updates.